Hi, everybody. My name is Ioana Cozmuta, and I am the co-founder and CEO of GSpace. And I will be talking today about designing materials without gravity. Historically, the evolution of materials has a very, very interesting trajectory. In prehistoric times to the 19th century, we pretty much focused our attention on what we call very simple natural materials such as wood, metal, and maybe some kind of alloying. But it is really over the past 100 years, so to present day, that we've seen an explosion in the in the diversity of materials, where we evolve them into nanocomposites and smart materials and photoelectric conductive materials, where we combine material properties, material functionalities that traditionally have been unmatched. So, for example, metal is more solid, more conductive. Wood is more easy to work with. And so we combine these functionalities because now we were able to harness the understanding of these materials from both physics and chemistry perspective down to the nanoscale. And so here's where we come into play. GSpace comes into play. We're a company that aims to bring unobtainium to the realization. And the way we go about it is we plan on expanding this envelope even further. The materials, everybody who's currently looking in identifying new materials is looking in the spectrum of materials formulations that are stable under a gravitational force. And so naturally, in the R&D laboratories or in the current efforts, nobody's literally thinking, well, what if I take gravity away? What happens? How much can I expand? And what's the value of expanding into those formulations that, again, are not stable under a gravitational field, but become stable when you remove the gravitational force, and how much that can push, again, this structure, function, performance relationship even further. So we are really looking into achieving broader structural stability, more uniformity of this material down to the nanoscale, defect-free, and ultimately perfect performance. So we are really looking into expanding the phase diagram of these materials. And we're not only looking at that from a deep tech scientific perspective, but we, of course, keep in mind the market, the forces that shape the market, right? And just if you look at past evidence, every single new material, such as Kevlar or Scotch adhesive, they created, once they existed and the application started to build on these new materials, each of them created their own billion-dollar market. So our goal as a company is not only to bring these beautiful new materials and use the gravitational force as the design parameter in materials, but also to bring several of them and each of them to create their own billion-dollar market. So like I said, for example, Kevlar, right? I'm giving, again, more details into the Kevlar and to the Scotch tape. Kevlar, the market size was $4 billion. For Scotch tape, $5 billion. The commercial appeal of these materials was from high strength, lightweight. That's the trade-off between the two properties that Kevlar was able to couple, to moisture-proof and transparency, optical transparency in the case of Scotch tape. And like I said, once the material came to market, people have become, commercially and application-wise, very creative in terms of building more and more market uses, right? From automobile components, surf and other boards, military jackets, smartphone casing, spacecraft components, right? To on the Scotch tape side, sealing products, office products, protective films, insulation, and repairs. So again, the versatility and diversity of these materials is very impressive. And also it is impressive how little it is understood, because people usually use the products, but they don't necessarily make the connection to the importance of the R&D on the material side and on the fundamental side. Here's what we're looking at. We're looking at the demands of the digital age. And literally, we have come to the realization that materials are an innovation bottleneck. There is an immediate need for versatile materials, but not only that, also for shorter commercialization time. So here we give a couple of examples, right? So we have sensors that are mostly made out of stainless steel. However, some people may be allergic to that stainless steel. So are there some ways in which we can fine-tune those capabilities of the material to solve these issues? For example, on the phones, we talk about foldable phones, but our definition of foldable phones is actually very narrow. We think a foldable phone is only on one direction. But what if we can bring to the realization of material that's as thin as a piece of paper, and it truly can be folded on many different directions, and you can put it in your pocket, and then when you need it, you unfold it. That is truly true foldability. And what it would take to get there, it's not just an engineering problem. It really is a deep material science problem. Another example is the demands of digital age also translate in the huge amount of data that we now need to push through all across the globe, right? We see big companies such as Google and Facebook and etc. continuing to lay undersea water cables. And how much the current technology in those cables is going to be able to support the demands of VR and AI, it's questionable. When we introduce G-Space, we basically introduce a terrestrial AI platform for rapid prototyping and commercialization of gravity-independent new materials. So while ultimately at longer timelines, we do foresee that big volumes in terms of manufacturing this material will have to happen in Earth's orbit. The early stages of this process, we are tackling them through our secret sauce terrestrially. So we don't only want to bring unobtainium materials to market, but we want to very intelligently select the materials that enable high profit margin applications. And part of that quick timeline to commercialization, we need to make sure that we capture the materials value chain at origin. We make gravity an adjustable design parameter. What we do is we eliminate gravity terrestrially through a proprietary trade secret experimental process and a combination of trademark machine learning algorithms under our Atom software platform. And here's the way we envision working with customers, from R&D to materials manufacturers and to the incomers into space manufacturing. You have a material that you've been trying to develop its new functionalities, or you're really trying to understand the limitations of a gravitational assist manufacturing process. We want you to come to us, and we'll look into what does it mean, or what is the opportunity to expand accessing formulations of your materials outside of where you currently are looking, as well as how do we improve and optimize and basically make more profitable your material manufacturing process. And again, we always keep in mind that these G-Space materials would be optimized for specific applications and make sure that they would deliver strategic value to you as a customer. So our first class of products that we have on the US market is what we call heavy metal fluoride glasses. We currently have a suite of passive and active fibers, bulk glasses, fiber components, and modules, again, on the US market. a variety of zebilan and indium fluoride, primarily zebilan and indium fluoride materials. But we also have an exclusive custom rod, in particular for those who are looking into the space manufacturing of such products. And what we're actively pursuing is the next generation of exactly these products, so the new formulations and the next generation of these products with improved performance. So why heavy metal fluoride glasses? Why? What's the value of it? So if you go back to the electromagnetic spectrum coverage, pretty much right now we are very much we are reliant on silica-based materials. But if you look at the entire spectrum of wavelengths from 1 to 15 microns and beyond, there's different classes of material that expand this, that enable access to this spectrum from a sensing transmission perspective. So we're really looking at capabilities, developing and deploying products and capabilities beyond the current silica-driven market. So one example, and in particular the heavy metal fluoride glasses that we're talking about, it's this class of fluorides. We're looking in a spectrum of accessing a spectrum from 2 to 9 microns, but we do have opportunities to expand to the rest of the electromagnetic spectrum. And again, if you look at the growth of the photonics field and at the same time on the market size, all the sensing application, these opportunities and these classes of material become a non-trivial player. So I'm going to just give one example because there's many examples that we've identified and so on. But this one is in the public domain, and we actually published a paper at the SPIE Photonics West on breaking the silica ceiling. So, and I'm just going to talk about one parameter, the fiber optics transmission, right? Today, a single pair of silica fiber can carry about 20 terabyte per second using about 100 nanometer of bandwidth. And the distance is about 50 to 100 kilometers, requiring expensive amplification. I'll come back to that, right? Our material formulations that we will identify through our secret sauce will enable unprecedented ability to carry over 1,000 terabyte per second per fiber pair at a 50 time, up to 50 time improvement over silica, and with amplification required only after 1,000 kilometers or more. Going back to that transmission window for silica that I showed in the previous wavelength graph, there actually is, while when silica started to be used, the first window has been used for the transmission. Right now, the data transmission that's really supported is in the second and third window. But the problem with this is that the material itself has reached its pretty much a theoretical attenuation. That's a fixed attenuation of 0.2 dB per kilometer. And so pretty much everything right now is focused on developing smarter engineering and software solutions to extract even more out of a material that's inherently limited. So what does that translate into real life, right? Is basically, well, you have an undersea water cable, and then you require repeater because, again, with this 0.2 dB per kilometer, you can only push a signal so much. So then you have another repeater and another repeater and another repeater. And this is like, having a problem, a medical problem, and instead of really solving the underlying problem, you keep adding patches, right? And up to growing a family pack of infrastructure in this case that becomes extremely expensive to compensate, through this infrastructure to compensate for something that's inherently a material problem, right? The evolution of attenuation for silica is very interesting, and I'm showing here a graph comparing that attenuation with that of zebilan. Originally, when silica started to be used for fiber optics transmission, the zebilan was the front runner, But the industry decided to invest more on the silica side. It did start at 1,000 dB per kilometer, and it took 4 decades of investments to bring silica from that original performance to its theoretical best. So a reduction of 4 order of magnitude. And that constant improvement in the manufacturing process, raw material purity, and design of the preform and the fibers was what was kept being improved. Right now, actually, ZB-Land starts at an extremely competitive advantage at approximately 1 dB per kilometer. Not only that, but no matter what you do, silica will remain at this level. You can't push it more than 0.18 dB per kilometer, because that's what the material can offer. Versus on the ZB-Land side, you can really go another couple of orders of magnitude. So we actually, again, this is one example of what we can do through our software platform, where we can take and do these kind of assessments and predictions of improving material properties for again, different formulations of the material, and say, well, this is the kind of better attenuation that we can get if we do X, Y, and Z. So, for example, by using a combined suite of processes to push the performance to the theoretical best, we could achieve a maximum attenuation of ZB-Land, and that could carry 2 petabytes per second per fiber pair with amplification only required over 1,000 kilometers or more. The combination, the way to get here is a combination of terrestrial as well as space processing improvements. Here's an example of our Atom platform. As I said, we do have our internal way of performing measurements, performing this assessment, so that we can connect material properties with performance. And my message to you is that it's time to stop thinking evolutionary and start thinking revolutionary. And this is where GSpace comes into play. We start with, again, this terrestrial combination of software and experimental procedures, but ultimately we want to move into manufacturing high volume of unique market value traction formulations of materials through the utilization of satellites and free flyers into orbit. So for those of you who are familiar with Planet Labs, our goal is to be the Planet Lab of materials. So I very much thank you for your attention, and I wish you gravity-free regards, and I'll take questions.